Hi friends, welcome back to the channel. Today we are going to see a problem which was asked in GATE 2019. This is a question from the topic of engineering mechanics. In this problem you have a car, a very simplistic car, and we are asked to find out what are the reactions on the front wheels and the rear wheels. Everything is given, the distance is given, the height of the vehicle CG from the ground is given, the distance between the two wheels is given. So now the question boils down to evaluating these two reactions. These two reactions are represented over here as capital R under script little r, and here it is represented as RF. So the first question, this is a real life problem, and we all know car is not a two-dimensional object. It's a complete three-dimensional object. So here is one of the key skills of an engineer or a mechanical engineer in particular sets in. Can we reduce the problem to 2D, or can we reduce the problem further down to 1D? Because once you start working as an engineer, these skill sets are really keen for you to get an insight into your problem. How efficient are you to look at a complex system and then break it down to simpler system and then gain insight into it? So this kind of techniques are really useful once you get into industry. Now coming back to this problem, this is a three-dimensional problem, but this can be solved from a 2D framework, and the figure is shown over here. Now we can treat this as a 2D object undergoing translation along this direction. Let me call that direction as little x. Since this is a rigid body, the second assumption comes in. I am assuming my car to be a rigid body. We all know there are deformable components in an automobile, but we are not worried about that for the time being. That's part of an entirely different course or an entirely different subject that will be taken care in solid mechanics. We are looking at the rigid body mechanics because what we want to get out of this exercise is the reaction forces. We are not interested in the displacement of the car and all those stuff. So the assumption one, the problem is a 2D problem. We are treating the whole car as a 2D object. Assumption number two is that we are treating this object as a rigid body. Now how we are going to compute the reactions at the wheels? It's not very difficult, because for a 2D object in a plane, there are equations of motion that governs its behavior. In this case, the equations of motion are fairly straightforward. If you sum up the forces along the x direction, it should be equal to mass times the acceleration along the x direction. Newton's second law, nothing great in it. Similarly, if I sum up my forces along the y direction, you know this car is not flying, so if I sum up the forces along the y direction, I should better get a 0 on the right hand side. Now think what will be the third equation. Can we write in another equation, or are we done? Think about it for a minute, or a couple of seconds in fact. Okay, so there is another equation. You can also compute the moment about any point. Let it be any point, but in this particular example I am taking the moment about the CG. There are a lot of external forces, so list out the external forces, then compute the moment about the CG. If I sum it up, then I should get 0 here. This particular equation comes from the fact that our automobile or the car is not rotating. So we have three different equations which governs the motion of this particular system. Next step is to draw the free body diagram, using which we can detail out these three expressions. We can plug in the external forces into these three expressions and solve for these two unknowns, which are the reaction on the front wheel as well as the rear wheel. This is how the free body diagram of the whole system will look like. Apologies for this ground. Actually, in a free body diagram we should have removed these grounds, but the key takeaway is that you remove the ground and you replace the ground with the external forces that are acted on this particular car, as shown over here. So now we have two forces here, capital R and HR. So HR is the horizontal force that is acting on the car, which causes the car to move forward actually. Same thing for the front wheel as well. Now altogether we have around 5 forces acting on the system, isn't it? I think I got my numbers correct. So 2 over here, 2 over here, and the 1 force over here. So this is the free body diagram. Now it's fairly easy because we have identified what are the external forces that are acting on the system, and we have removed all the supports. So let's sum up the forces in the y direction. In the first place, I am assuming the positive direction along the y-axis to be the positive sense for the forces. Then we get weight capital W is equal to the sum of those two vertical reaction forces. Nothing great happens along the x direction. Now let's go ahead and sum up the forces. Now before we sum up the forces, let's take the moments about the CG of the vehicle. So as I am taking CG about the center of gravity, I am assuming counterclockwise moments to be positive. It's just a sign convention. You can always argue that why can't it be the other way around. For this case, it doesn't cause a lot of problem, but when you do real three-dimensional problems, it's always better to have a strong sense for the directions. Okay, now if I take the moment about CGs, there are 5 forces, but the weight doesn't cause any moment about CG because it is acting through CG. The other 4 forces do cause a moment about CG, which are written out here. If you're asking why there is a negative sign on over there, here, it's just because of the fact that this particular force will cause a clockwise moment, not the counterclockwise moment. Rest of things are simply plug and check. You need so I'm expanding this expression here, and I'm trying to write little r or capital R subscript little r in terms of capital R subscript little f. But I'm trying to relate both the vertical reaction forces acting on the wheels. I'm introducing a new parameter here, x, which is nothing but little x is equal to our 2 mu h divided by L, where mu is the coefficient of friction, h is the vertical distance from the ground to the vehicle CG, and L is the distance between the wheels. So now we are left with only one equation to apply. We haven't summed our forces along the x direction. We did sum our forces along the y direction. Later we computed the moment of the total system about the vehicle CG. Now let's sum up the forces along x direction. Before we go ahead, I would like to tell you there is a relationship that exists between this normal force and the horizontal force. It actually comes from the laws of friction. So we can write the horizontal friction HR is mu, coefficient of friction, times the normal force. It's actually only true when you are at the point of impending motion and all those things, but Assume that this is in Bohr-Shell. I'm not going to differentiate the kinetic coefficient of friction to the static coefficient of friction and all those. But for the time being, understand that there exists a relationship between the vertical force or a vertical reaction at a wheel to the horizontal force acting at the same point. Makes sense? Because that will help us to simplify the math down the line. Now, once we sum up the forces along the x direction, we arrive here. Now, invoking what I just said, I can write these horizontal forces in terms of the vertical forces using the friction law. Now, we have another expression in terms of these two quantities. But when we sum the moments about CG, we have a relationship that connects these two parameters. So bring in that expression, this equation can be further simplified. Rest of these things are simply plug and check. But you need to ensure that you don't get these numbers wrong, because at the end of the day you may lose out on minus 0.66 or 0.33 marks, which are very valuable. So you need to pay a little bit. You can take your own time to verify these maths and solve it at your own pace. And once you do all these things, you will get two expressions. You will get two expressions for those reaction forces, RF and little rr. Couple of checks that you can do is, especially once you have done a long sequence of mathematical operations and you arrive at a particular expression, couple of checks you can do. One is the dimensionality check. Just see over here whether this quantity has dimensions of force. Yes, it does, because little a and little g has the same units, acceleration, which is meter per second square. And this again gives you a non-dimensionless number, because this is the ratio of two distances. So in that way, this particular term has dimensions of Newton, which makes sense. And when we add these together, we are getting W, which again makes sense. So these are the few checks that you can do once you arrive at a final answer. So it was a good problem which will test your understanding of 2D kinematics. 2D kinetics, I would say. Kinematics is a slightly different topic. We use the principles of kinetics over here. So thanks for watching.